Now let's do some calculus with polar curves. How about the area under a curve? We haven't thought about what that might mean yet. So here's a polar curve, and I might say, well, I want the area from like here to there. So if I fill that in, that's kind of the equivalent of area under a curve. So in rectangular coordinates, we start with x equals this, go to x equals that. Here we're starting at one theta and going to another theta. So we can say from theta equals some starting value to theta equals some stopping value. Because we're treating theta as kind of our x variable or kind of our independent variable. So that's one way to think of it. And then we're just saying what area is contained between that initial ray at angle theta, at theta equals start, and the final ray at angle equals stop, and the polar curve is the boundary. Or we could say, well, what if we just have some shape that includes the origin? I'd just go from 0 to 2 pi, for example. This is seems like it's going to be pretty tricky. Like I wouldn't want to draw rectangles up and down here. So what can we do? Well, let's step back a sec and talk about what we already do know. Let's talk about area of a circle. I'm going to say a full circle. Hopefully you remember that the area is pi r squared. How about the area of a half circle, a semicircle? Well, that would be the area of the full circle times a half. How about the area of a quarter circle? Probably see where I'm going with this. Pi times r squared times 1/4. So what about a circular sector? With angle theta. So let's draw something like this. And then this length is r and that length is r as well. So that's called a circular sector, or pie slice, you could call it, or cake, depends on your preference. So how are we going to go from this idea of a full circle or half circle or quarter circle to some kind of arbitrary angle of something? Well, let's point out what the angle is here. What's the theta angle for a circular sector that describes a full circle? That'd be 2 pi. How about the theta for a circular sector that describes half a circle? That would be pi. And how about the for a quarter circle? That would be pi over 2, 90 degree, right? So let's think about how does the pi over 2 pi play into this formula? How does pi play into this formula? And it's not actually this pi here. It's more about the multiplier here, right? One thing that might help, I noticed this has a fraction on it, this has a fraction on it, but this does not have a fraction on it. It's feeling lonely. It wants a coefficient just like the others. What coefficient can we write there that's in the same pattern as these? How about 1 over 1? Seems to help. So what can we say about this? What can I do with 2 pi to get 1, do with pi to get a half, and do with pi over 2 to get a quarter? Well, we could say, what's the fraction that's going on? You could say it's 2 pi over 2 pi. That would give you 1. Here you could say it's pi over 2 pi. That would give you a half. And you could say pi over 2 divided by 2 pi, that would give you a quarter. So we're basically saying what percent of a circle is this? Is it a full circle? Is it a half circle, etc.? So the area of a circular sector would be pi r squared, just like before, and then multiply by what fraction of a circle we're doing out of 2 pi, the angle out of 2 pi. So it would be theta divided by 2 pi. Now you might notice that the pi's kind of cancel, so you can cancel those, write the 1 over 2 front as a half, do an r squared, and then theta like that. So that's the formula we're going to keep in mind, but here's where it comes from, which is also good. So what are we going to do to compute the area? Let's get a nice wiggly curve here. What am I going to do to compute the area of this thing? Well, one of the big things in calculus is take a big problem and divide it into smaller, easier problems. So I can divide it into, let me do this gently. I divide it into circular sectors and then find the area of each one. Sounds reasonable. What can I do? Let's talk about this circular, let's do this one. So this circular sector here, how much angle would you say is there? I wouldn't call it theta, I'd call it maybe delta theta or d theta, because it's supposed to be a small chunk. And then what's the radius of that? Well, it doesn't have just a single radius. I could use this radius here, or I could use this radius there. But as I take that d theta smaller and smaller, these 2 points are going to get closer to each other, and they're going to be basically the same radius. So here we could say take the average radius between the two, pretend that was kind of curved. We could say take the first radius, we could say take the second radius. That corresponds to kind of the right end method, trapezoid method, midpoint method, not midpoint actually, midpoint would be out here, but left, right, and trapezoid. So the end answer is when we do an integral, it doesn't matter which one you do because we're taking d theta so small that they all end up the same. So we'd say we've got 1 over 1/2 r of theta squared times d theta, and then we'd integrate that from theta equals some start value to theta equals some stop value. So how do you find the area contained by a polar curve? You square the radius, multiply it by 1/2, integrate that. Now here we've said, or we've only drawn it for a fairly simple curve. If we want to give ourselves headaches, which we probably don't want to do, we could say, well, what if I had some kind of spiral that did that, where I have more than one theta value? For that, you'd have to be very careful about what region are you talking about. So we're not going to worry about that to begin with, and maybe never. We'll see. In the next video, we'll go trying all this in spreadsheets.